Good afternoon, sir.
Okay, Narayani, this is I think ninth standard, right? So, but she is in 10th standard, I suppose. Yeah. Have you sent a wrong link or something? Just give it to check. And you are, I'm from, it's a little complicated, but Bihar, West Bengal, Jharkhand. Yeah, I went to Kota as well. Yeah. So you are from Rajasthan? Shiva, I have heard of it. Yeah, I have heard of it. Nice. All we are studying. So you are taking some subject or nice. Nice to meet you. Your name? Vidisha. Okay. Hi. So shall we start? Is it okay? Same thing is happening with my phone. I keep on dropping it all the time. All right.
I like that book. Narayani, are you there? Narayani?
Yes, sir, I'm there.
No, you have to come to the 10th class. This for 9th.
Okay, sir, just a second.
Yeah.
Hello.
Hi, this is Sumit. We'll start in a minute. Okay, let's wait for others to participate.
Okay, sir. Yes, sir.
Sure. Hi Tejaswini, I think you are supposed to join the 10th standard class. You are in 9th standard class. Hi, can you hear me? This is Sumit.
No, sir.
You are in 10th standard, right? Tejaswini. Okay, you. Let's wait for 5 more minutes and we'll start, okay? After 5 minutes, we'll start. Okay, guys, so we'll be starting the class now, okay? So in previous classes, we have learned how to find the value of G. All of you are here? Everyone can hear me? Can you just give? Yes? Okay. So, okay, so keep your mic on mute. If you have any doubt, you just ask me at that time, okay? And if my voice is not clear, just let me know, okay? And we have learned how to calculate the value of small g, right? This, that is equal to 9.81 meter per second square. And we have also learned this to how the value of g varies, right? Those also we have studied. So it varies with on the surface of earth as well. Like if you are on equator and if you are on pole, so the value of g will be different at different position. Okay. All right. So let's say this is our earth. The shape of earth is kind of similar to this, not exactly. Of course, I'm not very good at drawing. So let's make it something like this. Okay. Let's say now, let's say this is our equator. Okay, equator line, that is 0° latitude. Okay, so 0° latitude, which is also called equator. Now, this distance we will assume from here to here to be RE. Okay, and this is pole. So here, the distance from the center of earth is RP. Since we know small g is equal to capital G multiplied by mass of earth upon radius, right? square, radius square. Now see, radius in the denominator, that means G is inversely proportional to radius square, right? Now you see here RP is lesser than RE, right? That means the value of acceleration due to gravity at pole will be greater than acceleration due to gravity at Earth, oh sorry, equator, okay? And all are on the surface of Earth, right? That we have seen. This derivation we have already done. I'm just giving it a revision to you, okay? And when you calculate this value, it comes out to be 9.81 meter per second square, all right? So these calculations and all we have already done. So let's move on to, let's start first by solving one problem. Everyone can hear me?
Yes, sir.
Okay, so I think for some of the students, let's have the derivation that the variation of G with height, with altitude, okay? So because it has not been covered in one class, let's cover it here. And for those who have already covered, it will be a revision for you guys, okay? So variation of G, what is G? Acceleration due to gravity at an altitude h above the surface of Earth. Okay, so this derivation, let's see how we can find it. All right, everyone with me here?
Yes, sir.
Okay, good. So now let's draw a shape. Okay, so let's assume, right now we'll be assuming the Earth is circular. Okay, so let's say, let me erase this. Please excuse me, I've been using this software for the first time, so it will take me some time to settle with this. Just excuse me for that. Now let's say I'll draw a freehand point. Let's say this is Earth, okay, and this is the center of Earth. We are assuming Earth to be spherical here in this case. Okay, these are just assumptions. Okay, so that to make our calculations easy. Okay, now we all know that this radius is R, E, radius of Earth, and we know the value of radius of Earth is approximately equal to 6,400 kilometer, which will be equal to 6,400,000 meter. Okay, so this is the radius of Earth. All right, from the surface to the center of Earth. Okay, now let's say there is some particle, some ball there at an altitude h from the surface of Earth. Okay, so how much will be this distance? So this distance we are measuring as h. So how much will be this distance from here to here? So this will be RE plus h, radius of Earth plus the height above the surface, right? Because from here to here we know it is RE. Okay. Yes. All right. So let's say this is B. This is some particle which is B. Okay. And let's say the surface of Earth is represented by point A. Okay. Now, for this particle B, let's write the acceleration due to gravity. So acceleration due to gravity for this particle B at this altitude. Okay. So you can also write this as, if you want, you can write as altitude at this point. So altitude value of G at height h. Okay. So this will be equal to G m mass of Earth upon RE square. So right now R value is how much? R value is RE plus RE plus H whole square, because this is the altitude of this particle B. Value of acceleration due to gravity. Let me erase it from here. I think it won't be possible to write here. Okay. So this is your acceleration due to gravity at height h. Okay. Now we already know that acceleration due to gravity on the surface is given by gme upon re square. Okay. So let's say this is equation number 1 and let's say this is equation number 2. So what we can do, we can divide equation 2 with 1 or 1 with 2 or 2 with 1, any one you can. So let's write down here g upon, this is g at surface of earth upon gh. Okay, so this will be equal to, now let's write down, this is g me upon re square divided by g me upon re plus h whole square. So from here we can write g me upon re square multiplied by re plus h whole square upon g into me. Now we can cancel out these two here, right? So g upon g at altitude h. G is acceleration due to gravity, obviously. Okay. At height h, this will be equal to what? Re plus h upon re whole square. We can write like this. So this will be equal to 1 plus h upon re whole square. Now you see, h is always positive, h is always greater than 0, re is always greater than 0. That means h upon re, okay, and okay, one more condition is the radius of earth, okay, re is greater than h. Now see, the denominator is greater than the numerator. So therefore we can write h upon re will be lesser than 1 but greater than 0, right? Anybody is having any doubt here? Anyone? All good?
Sir, I have doubts, sir.
Yeah, tell me, please tell me.
Sir, like Earth, you said it's a geoid, no, sir. So it's flatter in the pole, no, sir. So the radius will differ when it's near to the pole, no, sir. Something like
Right?
that.
Listen. When we are doing this derivation, we are assuming it to be spherical. That's what I said in the beginning. We are assuming that the whole earth is spherical. Even if it is, you are taking at pole or equator, we are taking the same value right now here. Okay, if you can take this pole as well as equator, but the ratio will come out to be same. Okay, if you calculate the ratio, it will come out to be same. It will be just, let me finish this derivation. I will show you with pole and that as well. Okay, so this anybody is having doubt here in this part? I hope not. Okay, so 1 plus h upon re is what? It is always greater than 1. This will be always greater than 1, right? This value will always be greater than 1. So 1 plus h upon re whole square will also be greater than 1 square, which is again equal to 1. 1 square is 1, we know this, right? So no need to write. So it will be greater than 1. This means, what does this mean? This means g upon gh is greater than 1. That means g is greater than gh. Okay, that's what we needed to prove. Okay, so what I'm saying, on the surface of earth, the value of g is always greater. Okay, now coming to equator and pole. So if you are finding at pole, let's say at pole, so what equation you will get? You will get g upon g h. So this is g at pole. Okay, g at pole. So what you will get? 1 plus h upon radius of earth. What is happening? Radius of earth at pole. Okay, that's it. Same equation you are getting. See, you will get the same equation. If you want to write at equator, g equator upon gh is equal to 1 plus h upon radius of earth at equator square. That's it. And of course, we know acceleration due to gravity at pole is greater than acceleration due to gravity at equator. This we have already proved. Okay, so this is at pole, at equator. Okay, so that's how the variation of g will take place with altitude. All right. Okay, let's do one problem based on this. Suppose you are standing in, you are floating in air. Okay, somebody is floating in air. I don't know who is this guy. This can be a girl also. They wanted to become a Superman like
Oh.
that. Okay,
Sir,
can you-
Babu.
yeah, Babu Rao. Yes, exactly.
Babu.
Yeah, exactly. So, and is flying at a height of 100 meter. Okay, from the surface of Earth. Calculate g, the value of g at 100 meter. Can you do that? So I'll give you some information. So this is the radius of Earth and this is mass of Earth. So radius of Earth is equal to 6400,000 meter. Mass of Earth is 6 into 10 to the power of 24 kilogram. And acceleration due to gravity, capital G, sorry, universal gravitational constant is equal to 6.67 into 10 to the power of minus 11 Newton. Can anyone tell me the unit? Yesterday we have discussed this. Tell me the unit.
Unit M2 by K, gravity is the SI unit of G is nm2 by kg squared.
Okay, see, if for everyone, listen, suppose you forget the unit, what you will do, you will write the gravitational force, which is equal to G m upon r square. Okay. Here we don't know the unit of G, right? But we know the unit of force, that is Newton. This is equal to G. Let's keep it G because we don't know the unit. Mass we know is kilogram. So kilogram into kilogram will be kilogram square upon meter square, right? So from here you can find G is equal to Newton. Just cross multiply. Meter square upon kg square. Okay. So this is Newton meter square upon kilogram square. Now find out this G. Everyone find it out. Let's see how who can do it faster. You just need to use this one. Okay, which one? This one. So I'll just write it here. G at H is equal to capital G into ME upon RE plus H square. Use this formula and find out. Done? Anyone? Anyone finished?
No, sir.
Do it fast, do it fast. We have to cover a lot. See, you have all the values. You just need to substitute it, right? So I hope you can do it. 6.67 into 10 to the power of minus 11 into
Into 6 into 10 to the power 24 by 6400100.
So you can see, you can write this as 64 or 6.4 into 10 to the power of 1, 2, 3, 4, 5, 6 meter. Okay, so you can write that as well. 6.4 into 10 to the power of how much? 6
Sir.
whole square. Okay, can you write like this? Yeah, we can write like this. Okay. So this you can write 6.67 into 6 into, now this is 10 to the power of minus 11 plus 24. Okay. And this is 6.4 into 6.4 into 10 to the power of how much? 12. Okay. Let's assume, so what this calculation will approximately be equal to 1. Okay, so let's say this is 1 into 10 to the power of minus 11 plus 24 minus 12. How much is that? This is 1, so this is approximately
1, sir.
right, approximately equal to 10. Okay, but when you find out the answer, this will not be equal to 1. Can anyone tell me how much is this? 6.67 into 6 divided by 6.4 into 6.4. Can anyone tell me this?
So 1.
No, not 1. Anyone? So this value will be 9.7. Sorry, 0. Okay. 0.977 approximately. Okay. Got it? So this will approximately be equal to 9.7. 9.77 meter per second square. Now see, this is the value of G at height 100 meter, right? So this is the value of G when height is 100 meter. So how much we are getting? 9.77 and meter per second square. Now we know at surface of Earth, the value of G, how much is? It is surface 9.81, right? Meter per second square. Now you see, can you see that G at surface is greater than G at height, at some height H, right? Can you see this?
Yes, sir.
Okay. When you'll do the calculation, obviously you will get this answer. All right. Okay. Let's move ahead. Now, another topic is, next topic is variation of G of acceleration due to gravity due to depth D. Okay, so suppose you are going inside Earth, inside the surface of Earth, how the value of G will vary. Okay, so understand this one clearly.
Sir, the value of G will increase.
G will increase.
Yes, sir.
Okay, let's
So
see.
the gravitational force will decrease now, sir, due to the.
Okay, okay. So different people have different opinion. Let's see what is correct. Okay, shall we? Okay. See, in the beginning of the class, I said that gravitational force is a property of mass. Remember?
Yes, sir.
Mass. Okay. And we know mass is equal to volume multiplied by density.
Yes, sir.
Right? See, when you are doing the calculation above, see, like above the surface of Earth here. So there is no mass of Earth here, right? There is no Earth here now. At this position, there is no Earth. The Earth is here only, isn't it? Yes or no? Can you see that? Okay, let me explain it. Okay. See, when let's say, suppose this is Earth, okay? So when we are doing calculation above the surface of Earth, so the mass of Earth is only, the matter is here only, right? Whatever Earth is composed of, it is here at this point, which we are saying ME, mass of Earth, and it will have some density, right? Rho. So we are going to represent density by rho, okay? Density of Earth and volume of Earth, and this will be mass of Earth. Okay, is that fine? Or let's write small e, me, ve, rho e. This is pronounced as rho, rho. Okay, rho is density. Okay. Now, why do we have to write like that? Why? What's the reason that we are writing? Because when you are going inside the surface of Earth, okay, let's draw it. Suppose this is your Earth, and when you are digging a well here, and you are here at this position, now what volume you are covering? What volume of Earth? What effect of mass of Earth is taking into consideration? So this again is a sphere. Now we know this distance from this point to the surface is called the radius of Earth. Okay, and this one is how much? If suppose this is height, it is depth d. So how much will be this? O A will be how much?
Sir, RE minus D.
Yes. Okay. So OA, which is this, will be RE minus D. Okay. OA will be R. Now this is the radius at depth D. Can we write like that? Radius at depth D. Okay. Now, mass of Earth, we have already said. So mass of complete Earth, okay? Mass of Earth is equal to volume of Earth into density of Earth. Now, volume of Earth, that means Earth we are considering is a sphere. Actually, it is not, but for the calculation, we are considering it as a sphere. So, volume of sphere is 4/3 pi into r cube, re cube, sorry, not square, cube. Okay, into density of Earth. Fine. Now, this is mass of Earth. This is how we can write mass of Earth. Now, let's write the value of G in terms of density. So G at surface will be equal to, we know capital G into ME, right? ME upon RE square. So can we write this as G, capital G, ME, we can write 4/3 pi RE cube into rho E upon RE square. Now RE and RE square, we can cancel these two. So what will have? Acceleration due to gravity at surface of Earth will be G times 4/3 pi RE into rho E. Let this be question number 1. Now at depth D. So this is at surface of Earth. At surface of Earth. Okay. Now at depth D. Okay. So the depth D, what we will write? G D will be equal to capital G M mass of Earth at this at D, at depth D, upon radius of Earth at D. So we have already written it as RD. Okay, we have already assumed this as RD here. See RD. Okay, so RD is RE minus D square. Okay, now we can write this as G. Now mass of Earth at depth D will be 4/3 pi r cube. Now what is the radius at here at this point? This RE minus D. 4/3 pi r cube, that means RD cube into density of Earth. See, density of Earth will remain same. Density will not change. Okay, either it is at surface. Like if you take a piece of chalk So the density at any point of the chalk is same, right? Even if you break the chalk, the density of chalk will remain same. So whole divided by RD square. So again, we can cancel out this. Now we can write GD is equal to capital G 4 by 3 pi RD into rho density of earth. Let this be question number 2. Now when you divide 1 by 2, 1 by 2. So what we'll get? G upon G at surface upon G at depth D will be equal to capital G. So let's write this one, capital G 4 by 3 pi RE into rho E whole divided by G into 4 by 3 pi RD into rho E. Rho E is the density of earth. So this G will cancel 4 by 3 pi R rho E. So what we are left with? RE upon RD. Okay. So what we'll have? So from here we can write okay, just a minute guys, I'm not able to write, I don't know. Okay, all right. So we can write G S upon GD will be equal to RE upon RD. Okay, and RE, let's keep it as it is, and RD we know is how much? See, RD here we have assumed RE minus D. RE minus D. Okay. So can we write, we can take the inverse. So writing this again. So we can write G at depth D upon G at the surface will be equal to RE minus D upon RE. Okay. So this we can write 1 minus D upon RE. All right. So now see, D is positive, is greater than 0. RE is greater than 0 and RE is greater than D. Okay. That means this D upon RE will be lesser than what? 1, because the denominator is greater. So this will be lesser than 1. So if this is lesser than 1, that means this 1 minus D upon RE will be what? Lesser than 1. Okay. That means G at depth D is lesser than G at, because this is equal to GD upon GS. Okay, so this will be GS. So GD, that means at depth D. Okay, now let's understand. At this depth D at point A, the value of G is lesser as compared to the surface. That means what? That means even if you have, let's say if this is the surface of Earth, okay. So if suppose this is Earth, surface of Earth, and this is the surface, right? This is some depth D. So this is RE minus D. This is RE, and this is some height, let's say H, okay, above the surface of Earth. So the value of G at the surface of Earth, at the surface, is greater than G at height, and also G surface is greater than G at some depth T. Okay, so how it varies? Let's see the variation. If we plot, let's say this origin represents the center of Earth. Okay, let's say this origin represents the center of Earth, something like this. Okay, so if this is Earth, this is origin. So this distance is how much? This coordinate will be how much? Because this is the radius of Earth. So let's write RE, 0. Okay. Now we know the value. This y-axis we have acceleration due to gravity in meter per second square. Okay, and here this is in meter because this is R, radius. Now at the surface of Earth, the value of G is maximum. Okay, so at surface of Earth, the value of G is maximum, which is 9.81 meter per second square at surface. Okay, and at center, the value of G is 0. So it increases like this. As you move towards center, the value of G will keep on increasing. And as you go above, what will happen? It will start to decrease again. Okay, so it start to decrease exponentially. And it increases when you are going from center to the surface. Okay, that's what is the variation of G with respect to the Earth. So this is Earth. Okay, I hope this is clear to you all. Yes. So what is the difference between, like, we have learned a lot about small g and capital G, right? Small g and capital G. So this is called your universal gravitational constant. And this is called your acceleration due to gravity. Okay. So what's the difference between these 2 points? So write down the difference. So the first difference is, okay, or maybe not just the difference. The first point, let's say, in acceleration due to gravity, it is the acceleration acquired by a body due to the Earth's gravitational pull. See, because on Earth, it will you will all the bodies will have a gravitational pull towards the center of Earth, and because of that, we have a weight force, right? Weight force, and that weight force is a property of mass and acceleration due to gravity. So that gravity we are calling is small g. Okay, I hope, see, this is there in your book in page number 93. Okay, page number 93, your MTG book, the difference is given. Okay, I'll just describe one by one. See, this g, small g, is a vector quantity. Okay, you have to understand, because it is acceleration, right? And acceleration is vector. Small g is a vector quantity, but capital G is a scalar quantity. Okay, it's a scalar quantity, and its value is 6.67 into 10 to the power of minus 11 Newton meter square upon kg square. Its value is 9.81 meter per second square. Okay. Yes. Now, yeah. So value of G, small g, at the center of Earth is 0. That means the value of G keeps on varying, right? Keep varying with position. And capital G, the value will never change. So I'll write the value will be constant throughout the universe. Okay, so these are the differences between small g and capital G. Okay, so let's move on to another topic. Okay, see there is one more topic, that is the variation of g with the rotation of earth. Means if the earth is rotating, the value of g will also vary, but let's not go into that equation. Okay, I think these 3 points are more than enough. You will study that later. So next is our equation of motion for a body moving under gravity. Equation of, we have already studied this in first chapter, you know, how the value of g will take positive or negative is the same thing. Okay. Now, see the general equation of motion, we know 3 general of equation of motion is v is equal to u plus at. Okay, s is equal to ut plus half at square, and v square minus u square is equal to 2as. Fine, we know all this. Now for a freely falling body, for if the body is freely falling, for free fall. Free fall means what? Suppose you took a body, a stone to the tower, okay, some tower, and you leave this stone from here. So it is falling freely, right? So that is called freely. So the equation will be v is equal to u plus gt. Now you will replace a is equal to g. Okay, so s, or if this is h, the height of tower. Okay, so you will write h is equal to ut plus half gt square, and v square. So this is the initial velocity u, the final velocity will be v square u square is equal to 2g into s. S is h here. Okay, I hope this is clear. See, the value of g, or the sign of g, small g, it always depends on the sign of s. If s is positive, g is positive. If s is negative, g is negative. What do we mean by that? I've explained this in classes, right? I suppose I have done this. Remember in first chapter itself, I have done this, right?
Like opposite direction
See,
in the
suppose,
graph.
see, when you are doing the calculation, you are taking the origin at this point, right? You are taking origin here. That means here, in the downward direction, you are taking positive direction. Okay, that's why g is positive here. In the upward direction, you are taking it negative, because you, the height you are taking here, you are not taking minus h, you are taking plus h, right? So that's why the value of g is also plus. Suppose the origin was here, okay, and your body is falling from this altitude to downward direction. So it is falling by a height of minus h. So at that time, you will take g as negative. Okay, so don't confuse. Whatever value of, just remember this, whatever value of s you will take, same sign, sorry, not value, sign of g you will take. Okay, that's it. If you can understand this much, I think you don't have to memorize anything. All right. Now see, in your book, I have written this according to your book, but I think it will be better if we solve a problem. Okay, so let's solve a problem. Now, the problem is, okay, so it's in page number 95 of your book. A helicopter is ascending with a velocity of 2 meters per second at height of 24 meters. That means now there is a helicopter. Okay, let's something, I don't know. Maybe like that. Okay, and who is this? Babu Rao.
Bhavanath sir. Yes.
Babu Nath.
Yes, sir.
Babu
Babu.
Nath. Babu Nath. Babu Nath is very famous guy. I want to be famous, but not as much as Babu Nath. Okay, Babu. So,
Sir, Babu Nath is not in the class, sir.
oh, he's not in class. Oh, wow.
Sir, he's eating, sir. I just called him.
Okay, cool. So it's fine. So let's say this helicopter is moving with a velocity of 2 meters per second. Okay. And it is at a height of 24 meters. It's a very less height. It's flying very low. Okay. So 24 meters when it drops a packet. That means in a helicopter, there is a packet. This guy, Babu Nath, is dropping this packet. Okay. See, when he is dropping this packet, that means it will have a free fall. The packet will be freely falling. There will be no obligation on the packet. Just gravity will be acting on that packet, right? So see, in the problem it is given the packet contains material which can be damaged, like some fragile item is there in the packet. Okay, when it hits the ground with a velocity greater than, so if the final velocity is greater than 72 kilometer per hour, the packet will get damaged. Okay, so you have to tell whether the packet got damaged or not. Okay, and G is, you have to consider 10 meter per second square. Find it? Understood the problem? The helicopter is moving with a velocity, ascending, sorry. It's not in that direction, it's ascending. That means in this direction. 2 meter per second. Okay. So you have to find the final velocity. Use this equation of motion. Where is this? These equation of motion and find out what is the final velocity. Solved anyone? See, velocity, that means initial velocity is given, right? Which is minus 2 meter per second. Why minus? Because it is in the
Sir,
downward.
I got that v square is equal to 484, sir. But when the square goes to the other side, it will be like root 484, no, sir.
Yeah,
Proceed. Right.
do that.
We can write 484 as 2 root 121. Till that only we can solve, sir. So V will
Okay,
be.
so we can use this equation of motion. Can we use this?
Yes, sir.
So from here we can directly find V. So V square, you have also used this equation, right? Minus, and the velocity is -2 because it is falling in the downward direction. That's why it is negative, right? Okay, into 2, and G will be what? Positive or negative?
Sir, positive, right?
Positive. Why? Because we are considering origin here. We are considering this height as positive, right? That's why
It's
G,
positive. Yes, sir.
if you consider H as negative, G will be negative. Okay,
Yes, sir.
so we can do that as well. If you take G negative, -10, you have to take H also negative, -24. -24. Okay, you will get the same answer.
So
Okay,
from ground we are throwing it up, so we can use this like.
yeah. No, it's not about you are throwing from ground or away from ground, matlab, onto the ground. It depends upon where you are taking the origin. Okay, the coordinate system. Where is your reference point? Okay, that matters. It doesn't matter whether you are throwing the ball up or it is falling down. It's just written in your book. Okay, it's just there in the book so that you can memorize it. But I will never suggest you to memorize. I'll just tell you to follow this. If S is positive, okay, if S is positive, your G will be positive. If S is negative, G is negative. That's it. Okay, so both will have same sign. So this will come out to be 484 meter square per second square. Okay, so from here you can get velocity. V will be equal to square root of 484 meter per second, because you will again put the square root over here also, no? That's why. Okay. 484 meter per second square. So this will be equal to, let's write down. So V will be equal to 22 meter per second. Is there in the book? I'm just writing it down. Okay, so this is not meter per second square, this is meter per second. Okay, it's the same example I'm taking. So from here, now convert, see, since the unit here, what is given in the problem, that if it hits the ground with a velocity greater than this, then the package will break. So it is in kilometer per hour. Either you can convert this in meter per second or convert this velocity in kilometer per hour. So let's convert this in kilometer per hour. So V will be equal to 22. In 1 meter, we have 1/1000 kilometer, right? And in 1 second, we have how much? 360, 1/3600 hour. Okay, so this will come out to be 79.2, approximately 79.2 kilometer per hour. So is the value I'm taking directly from book. Okay, see, since the velocity it is hitting with is what, v is greater than this 72, right? That means the package will break. Okay, so you can write the answer, because the packet hits the ground with a velocity greater than, okay, so let's write down, because the packet hits the ground with a velocity greater than 72 kilometer per hour, the packet will damage.
Sir, can you teach conversion, sir? I don't understand that one.
Which one?
We got the V now, sir. Then you converted it now, sir.
Okay, fine. Let's do it again. See, in 1 kilometer, sorry, kilogram I'm writing, kilometer it is. In 1 kilometer, we have 1000 meter, and in 1 hour, we have how much?
60 minutes.
Why I'm doing this mistake? Okay, that means in 1 meter, we have 1/1000 kilometer. Okay.
Yes, sir.
Now this is clear. Now in 1 hour, we have 3600 second. That means in 1 second, we have 1 upon 3600 hour. Fine.
Yes, sir.
Okay. Now let's do it here. Okay. Let's do it again. Sorry. Let's convert it again. Now can we write this as meter upon second, meter per second, right? So
Yes,
this
sir.
is equal to 22. Now meter will take from here meter to kilometer, right? So can we write this as 1 upon 1000 kilometer? I'm writing this meter. Can we write this?
Yes, sir.
Okay. Now the second, we'll write it here. So this will be equal to into 1 upon second, right? So 1 upon second. In 1 second, how many hours? 1 upon 3600 hour. Fine.
Fine, sir. Yes, sir.
Okay. So can we write this as V is equal to 22 now multiplied by, so this is 1 upon 1000 into, so can we write this as 3600? This will go up, isn't it?
Yes.
So we'll write the unit together, kilometer per hour. So
Sir,
that's
we'll
how,
get 5 by 18 now, sir.
what?
We'll get 18 by 5, 5 by 18. One
Yeah,
value.
yeah,
Yes, sir.
exactly. You'll get 18 by 5. So you multiply by 22, you'll get 79.2. So let's write 79.2 kilometer per hour. Now is it clear?
Yes, sir. Clear, sir.
Okay, very good. So we'll end the class here. Okay, and I think till 2 o'clock only we had class, right? Or 2:30.
Sir, I really don't know. They haven't mentioned the time, sir.
So actually, in the announcement, it's given as 1 to 4 o'clock, sir, but I don't know, sir.
Okay, see one.
Sir, it's still 2:30, and then we have math from 2:30 to 4 o'clock.
So 2:30 till 2:30, right? So let me get some water, then I'll continue again. Okay. Is that okay? So till now, can you turn on your page number? Okay. Before just solve this problem. Page number. Page number. Okay, page number 9. No, not 9. Sorry. Page number 109.
Okay, sir. Yes, sir.
Page number 109. Okay, question number 17, 18, 19, 20, 21. Solve these 4 and we'll solve these questions first. Okay, and then we'll move ahead. I'll take some water, then I will be back.
Yes.
So are you able to solve this? We have discussed all this problem before. Huh? Anyone? Question number 17. Let's do first question number 17.
Sir, it's option D, sir, both A and B.
Both A and B, okay. The type of force that exists between two charged bodies. Okay. So there are two bodies, charged bodies. Let's say positive charge and negative charge. So will it be only gravitational or only electrostatic? See, because it is having charges, so there will definitely be an electrostatic, right?
Yes, sir. Yes, sir.
But it will also have mass, right? Because it's a particle, so it will have a mass, and those who has mass will have a gravitational force between them. Okay, so it will have both. Both A and B are correct. Okay, 17. How about 18?
Sir, B, sir, attractive force.
Gravitational force is repulsive force, attractive force, or both?
Attractive.
So we have studied this gravitational force is only attractive force, right? Okay. So what about 19? Anyone is having doubt, just stop me, okay? If r is the radius of Earth, the height at which the weight of the body become 1/4. Its weight on this. Okay, we haven't discussed this. Next topic is that. How about 20? So question number 19 will still have to do. So let's leave it. If the diameter of the Earth becomes 2 times its present value, we have done this problem in school, right? Its mass remains unchanged, then how would the weight of an object on the surface of Earth be affected? See, weight is a force on surface of Earth is equal to gravitational force. Okay. So whatever changes will be there in gravitational force, same changes will happen. Now we know gravitational force is directly proportional to the product of masses and inversely proportional to the square of distance between them. Here it is said the mass is not changing. We are changing the diameter of Earth. Okay, so from D it becomes 2D. So we can write F is proportional to 1 upon D square because these two are again constant. Okay, so FG so FG1 is proportional to 1 upon D1 square. FG2 is proportional to 1 upon D2 square, and D2 is 2 times of D1 square. So FG2 will be proportional to 1 upon 4D1 square. Now let's say this is 1 and 2. So if you divide 1 by 2, what you will get? Fg1 upon Fg2 will be equal to 4. That means the Fg2 becomes 1/4 of Fg1, right, which is equal to weight. So weight upon 4. Okay, so fourth of weight 1/4. So weight will become 1/4. That is B is the correct option. Option B is correct. Now 21. Which of the following, which of the given graph correctly represent the variation of G on Earth? So I've already drawn this curve, right? So if this is G and this is R, so first it will vary linearly. I don't know why it is not linear. It will be linear in the beginning. Okay, then it will be exponentially, it will decrease. And it is maximum at radius surface of Earth, okay, which is 9.81 meter per second square. This is center of Earth. Okay, so Option A is the correct choice. All right. So these questions we have done. Now let's move ahead and study something. Study about mass and weight. We already know this, mass and weight. So what's the relation between mass and weight? Anyone?
So weight is the calculation of force exerted on an object like gravitation.
Yeah. Mass is the amount of matter contained in a body, right? Suppose there is some. So the amount of matter that this body contains will form the mass of this body. Okay. And this mass will have, and this body will have a center where it will be assumed all the mass of this body is acting. Okay, it is assumed. It is not, but it is being assumed like that. Okay, so mass, that means mass do not have any direction. So mass is a scalar quantity. Okay, now weight is a force which is the product of mass, the scalar quantity, into acceleration due to gravity, right? And we know acceleration due to gravity is a vector quantity which is directed towards the center of Earth. So if this is Earth, this is the center of Earth, and if you are standing here, that means your mass is your weight is acting in this direction, because G is also acting in this direction. So weight is a vector quantity. Okay. Okay, so weight is a vector quantity and weight is a force, type of force. All right, isn't it? Yes or no? So the SI unit of mass is kilogram, and SI unit of weight is what? Kilogram meter per second square, which is Newton. Fine. Yes or no? Anyone? Please.
Yes, sir.
Finally, somebody said. So you see, if you increase the mass of a body, the weight of the object, the weight force will also increase, right? Because weight is directly proportional to mass, isn't it? And also weight is directly proportional to G, isn't it? If you are on the surface, that means weight of a body is maximum on the surface of Earth. Weight of a body is maximum on the surface of Earth. Why? Because on surface the value of G is maximum. Okay. At surface the value of G is maximum, and weight is the product of mass and G. Now see, you go anywhere in space, mass will remain constant. Okay, unless something is leaking out, like in rocket. What happens? When it takes the satellite up, it will be, the fuel will be continuously burning, right? So at that time mass will keep on decreasing. Okay, so that is different case, but a solid body will have the same mass throughout the universe. Okay, in case of rocket, the fuels will be burning, right? Like if you have the gas cylinder in your home, or the gas will come, how you are burning that gas, right? So the cylinder is getting empty, isn't it? So that's how the mass of the mass of the cylinder will keep on decreasing, because the gas is getting out of it all the time. So that's what is happening. That time mass is decreasing. Otherwise, the mass will remain constant. Okay, so let's take mass as constant. All right. So I suppose these are the most important points that you need to understand. See, that means, of course, if you take this Earth and you are at pole, so the weight, your weight at pole will be greater as compared to your weight at equator. or did I said ulta? Right? You will weight more on pole as compared to on equator. Got it?
Yes.
Now, yeah. Any doubt? Anyone having any doubt?
No.
Because see, the G value, this G at pole is greater than G at equator, right? That's why weight is equal to what? M into G. M will remain constant. So weight at pole will be greater than weight at equator. That's the reason. Okay. So the next topic: how do you calculate weight of an object on the surface of moon? So let's write down weight of. Anybody is writing down anything, or you're just watching this? Weight of an. See, you will only learn if you keep writing. Okay. Object on the surface of moon. Till now we have made all the calculation on surface of earth. Now we'll do on surface of moon. Okay, since we know the gravitational force is an attracting force, so F, let's write F is equal to G m upon r square. This is a general equation of what? Force. Okay, gravitational force between any two masses. Okay. Now on surface of earth, we have seen weight is equal to force. Weight is equal to gravitational force. That's what we have seen. Right? Yes or no?
Yes, sir.
Okay. Now what we'll do, we'll take the, and weight we know is M into G. Right? Now what we'll do, we'll take this mass to moon. Okay. We'll take this mass to moon. What will happen then? So let's write the force, gravitational force on the surface of moon. So G, M mass of moon into this small mass M upon R radius of moon square. Okay, we are writing on the surface of moon. Okay, where let's be right, mm is the mass of moon. Okay, and m is the mass of object. Okay, rm is the radius of moon. All right. Okay, so weight on the surface of moon, weight on moon will be equal to this force. So this will be equal to Wm. Weight on moon. So Gmm upon m into Rm square. Okay. This is mass of moon. Okay, and this is mass of object. Let's not get confused. Now let's say this is equation number 1. We have already assumed. So this is equation number 2. Now if we divide equation number 1 with equation number 2, what can we write? Let's write, or 2 with 1. So mass weight on the surface of moon divided by weight on earth will be equal to, let's write down. So this is G mass of moon multiplied by the mass of object divided by Rm square multiplied by weight of 1 upon weight of earth, object on earth. So this is this value. So this is Gmm upon R square. This will be Gmm upon R square. Okay. So this R square we can take up R square. And this R is the radius of earth, mass of earth. Okay. So let's write like that. Mass of earth, radius of earth. Okay. So that's the better understanding. That will give you the better understanding. Let me add a page. Okay. So what we will get
Sir,
from here?
sir, I have a doubt.
Yeah, please tell me.
So we're dividing the weight of an object on the moon by the weight of an object on Earth, right?
Yes.
Okay, so I don't understand what the formula that you gave us for weight on moon.
Okay, see, let's understand using a diagram. Okay, so suppose this is the moon. Okay, and some object is there on the surface of moon. Okay, this is having mass m. All right, now what is weight? Weight is the force acting towards the center. Right now we are on moon. Okay, isn't it? So
Yes,
this
sir.
will be weight of moon. So weight of moon. So weight of any object on the surface of that object is equal to the gravitational attraction force. So weight, we know, we can write mass into g of moon, right?
Yes, sir.
And gravitational force is equal to mass of moon multiplied by mass of the object divided by g, this r square. So this is the radius of moon. Sorry, rm. So rm square into g, capital G. Is this fine?
Yes, sir.
Now we know if the object is on the surface, its weight force is equal to gravitational force. Okay, so let me write the statement: on the surface of moon or earth or any planet, okay, or any object. I'm writing moon because we are studying about moon here. Okay, moon, on the surface of moon, the weight of the object, weight is a force. So let me write in bracket force is equal to its gravitational force between those two objects, means between the moon and object. Okay, that is this one. Okay, is that okay?
Okay. Yes, sir.
Okay, this we need to understand. I haven't written this before, so I'm sorry. Now you got it. Why we can write this equation number 2, and
Yes,
right
sir.
now we are just dividing equation 2 by 1. We are just dividing equation number 2 by equation number 1, so we will get this. So from here we can write. Is this thing clear to everyone? So weight on the surface of moon divided by weight on earth. So you can write WE also. If you would like, you can write WE. Okay. Here you can write WE. That's just for the representation on earth. So this we have got. Now from here, this G will remain constant, so it will get cancelled. Okay, this mass will also get cancelled because we are taking the same mass on earth and same mass on moon. So what we are left with? Mass of moon, fine. Yes, divided by mass of earth multiplied by radius of earth square upon radius of moon square. Okay, now we have these values like mass of moon. So mass of moon has been calculated to be like 7.4 into 10 to the power of 22 kilogram. Okay, mass of earth I have already written it before, 6 into 10 to the power of 24 kilogram. That means earth is almost 100 times heavier than moon, right? Now radius of earth, I told you 6400 kilometer or 6400,000 meter, because meter is the SI unit, that's why I'm writing. You can write 6.4 into 10 to the power of 6 meter. Radius of moon is equal to 1.74. I'm using the value that is given in book. Okay, meter. Now if you substitute these values here, what you will get? You'll get weight on moon upon weight on earth is equal to 1/6. Okay. This you will get. Now we know that weight of moon is equal, weight on the surface of moon is equal to mass into acceleration due to gravity on moon, and weight on earth is equal to mass into acceleration due to gravity on surface of earth, right? So if we substitute these two here, what we'll get? So let's write m into g on moon upon m into g on earth is equal to 1 upon 6. So this will get cancelled out. That means this gives you, so acceleration due to gravity on moon is 1 upon 6 times the acceleration due to gravity on earth. Okay, that means, and we know acceleration due to gravity on earth is how much? Huh? How much is acceleration due to gravity on earth? Surface of earth.
9.81, sir.
9.81 meter. Always unit is important. Okay, so 9.81 meter per second square. So if you divide 9.81 by 6, that will give you the what?
Gravity in a moon.
Yeah. Okay, got it?
Yes, sir.
Okay. See, there is a question on page number 97. You can try to solve that question. Okay, it's illustration 7. It's a solved example 7 and 8, and hopefully it will be easier for you to understand if these concepts are clear. Tomorrow in our class, we'll be studying Kepler's law of planetary motion, and we'll try to finish this chapter and solve some of the problems. Okay, so if you have problems in this chapter, just tell me. Tomorrow you can tell me. Okay, so we can solve it together. And next chapter is going to be thrust and pressure. Okay. All right.
Yes, sir.
Okay, sir.
Thank you so much. Tata. Bye bye.
Thank you, sir.
Bye-bye, sir.
Thank you, sir.
Thank you so much.
Thank you, sir.